Hello, my name is Abhishek and I am part of a three-member team. Myself, Abhishek, and my partners are Yashwant and Krishna Sai, and we are doing this video lecture for the course Computer Organization and Architecture by Professor Dhanbal. Okay, here we start with the video. The topic is IEEE 754 Standard Floating Point System. Here we are first of all representing the numbers in scientific form. For that, the rule is a number, then a decimal point, and the rest of the digits multiplied by exponents. Okay, here we take an example of this number 257000. To represent this number in the scientific form, from the rule, we have to place there should be only one number before a point. So 257000, it can be represented as 25.7, and all these zeros are here we have written as 10 power 4. And now second example 2.57, we can write this as 25.7 into 10 to the power minus 1. Here we consider this one 3.14. It's already in normal scientific form, so we are writing it as 10 power 0. It can also be represented as 31.4 and 10 to the power minus 1. Now we take an example of this number 387.33. As per the rule, there should be only one number preceding 0. So we take this 2 points to the left. It becomes 3.87 and 10 square. Then 0.0063. Here we bring it 2 points to the right and it becomes 6.3 into 10 to the minus 3. Now we do the same for binary numbers. For example, 101.11. Here also, as per the rule, there should be only one digit before the decimal. So it becomes 1.0111 into, here it's the base. As it is a binary number system, there are only two numbers, zeros and 1. So the base becomes 2. And here we have shifted the point 2 digits to the right. Therefore, the exponent is how many points we are shifting the decimal. Here we have shifted 2 points to the right. So it becomes 2 square. So here 1.0111 is in decimal form. Therefore it's in binary form, therefore we are writing the base 0 into, as it is binary form, the base becomes 2, and this power 2 can be written as 10 in decimal form by base 2. And to convert this 1.0111 into decimal system, we get this as 1 into 2 power 0. This is 2 power 0. After the decimal, it is 0 into first digit 2 power minus 1 plus 1 into 2 power minus 2, so on. We convert this into the decimal number and it becomes 5.75. Now I hand over it to my colleague Yashwant. He will take it from here.
Now we'll see about writing these numbers in floating point representation. First we'll see about 8-bit format. So this is the basic 8-bit format for floating point number. The first bit represents the sign, and the next 3 bits represent the exponent, and the last 5 bits represent the significant bits. So let us consider this example 1.011 into 2 power 2. So the sign of this number is positive, so we place the sign bit as 0, and the exponent of this number is 2, so we convert the 2 into 3-digit number, that is 010, and we place it in exponent bits, and the significant bits are 0111. This is the basic 8-bit format which we are going to represent. Coming to suppose we got negative numbers are exponents, so we'll add some value known as bias. Suppose here we are taking 3-digit exponent number, so we should add the bias as plus 3. Take this example 1 into 2 power minus 1. So here my exponent is minus 1. Since we are representing this exponent in 3-digit format, we should add bias as minus 1 plus 3, that is 2, and 2 is converted into binary, and this is placed in this exponent. So the final number becomes 0, 0, 1, 0 and 4 zeros. So this is the basic formula for bias. So here when we are considering 3-bit exponent, that is 2 power 3 minus 1 minus 2 power 3 minus 1, that is 2 square minus 1, that is 3. So bias is 3. Floating point number can also be represented in 32 bits and 64-bit number. This is the basic 32-bit standard form, sign, and 8 bits exponent, and 23 bit significant bits, and 64-bit standard form is sign, 11 bits, and 52-bit significant bits. So bias for 32-bit is bias for 32-bit is 127, and bias we should add for 64-bit is 1023. So this is conversion of decimal to floating point. Consider decimal number 0.5625. Now we can convert by basically multiplying 2 and taking the remainder, and we'll place it here. So this is the basic binary form, and we can convert it to the floating point using this standard form as earlier mentioned. So coming to floating point to decimal, there is some specific formula to convert this floating point to decimal. This is the formula: -1 whole power sign into 1 point significant digits into 2 power e minus 3. So okay, now my friend Krishna Sai will continue the video.
Hello, my name is Krishna Sai. I am also a part of this group. Now I will explain floating point to decimal. Here, as my friend said, there is a certain format for converting floating point to decimal. Here it is mentioned sign into 1 point significant into 2 power exponent. So here there is an example: -1 to the power sign into 1 dot significant into 2 into e to the power -3. Suppose this is the example we take, like 1.001 into 2 to the power -1. Now to convert this -1 into power sign, this is a positive number, so the sign becomes 0. If it's a negative number, the sign becomes -1. 0 into 1.001. Significance is, this is the significant part, so 001. Here 1.001 we have written into 2 to the power -1, which is from 2 to the power e power -1. Here the value of 010, it's 2, so e to the power 2 minus 1, so e to the power -1. So from this we simplify it and we get this as 0.5005, which is not at all equal to our original number 0.5625. So doing this in this method is wrong. So here we have represented the correct way. So -1 to the power 0 becomes 1 into 1 dot significance. While calculating significance, we do not take the value here direct. We don't take the digits present here. It is 2 to the power -1. Next one is 2 to the power -2, and next one is 2 to the power -3, and here we have a 1, so it becomes 2 to the power -3, which is 0.125. So in place of significance, we have to calculate the value and place it here into 0.25, which is exactly the answer. So this is the correct way of doing. Now we have some special cases. Here the all the exponent bits are 1, 3 exponent bits 1 1 1, and all the significant bits are zeros. And two such cases are possible: all significants are 1, all significants 0, all exponents are 1. Here also all significant bits are 0 and exponents are 1. Sign is 1, here sign is 0. Sign is 0 we have taken for positive numbers, and this one represents the positive infinity, and this one represents the negative infinity. Now the next case, where here all three are 1s, but here it is a non-zero number, then we call it as NaN, which will be explained following. If the exponent bits are all 1, here see all exponent bits are 1, and the significance is a non-zero number, then it is called NaN, means not a real number. Examples are root of -5, 0/0 form, which are not defined in real numbers. So now we are trying to find out the largest number which can be represented in this format. So this is 8-bit format of this. First one is this first three digits. The last digit, the least significant digit, we are placing a 0, and the other 2 digits we are placing a 1. And in this position all we are placing 1s, because we need the largest number that can be represented in this form. As the sign is 0, -1 to the power 0 into 1 point, all 4, the significance is 1 1 1 1 1 into 2 to the power 3 to the power 3. How did we get this? E power -1. Here the number is 6. 6 minus 3 is 3. So the final value is this. Next, for 32-bit, we are finding the largest which we can represent. Here also it seems to follows the same method. The least significant bit becomes 0 and remaining everything else is 1. By solving this, we get is as 1.70 something into 10 to the power 34. Similarly, it can be done for 64 bits also. Denormalized, that's it. So that's it for the video we are doing. Thank you.